Hi everyone, let's get started. Can those of you at that end hear me okay? Cool? What about on this side? It's all good? Okay, cool. So let's get started. I'm Prashant Anantharaman, and a little bit about myself. I recently started as a senior security researcher at NARF Industries, which is a security research and consulting company that mostly does work for the US government. And we've also recently started looking a bit deeper into industrial control system security. So if that's something that you guys do, then you should come and talk to me. So I currently reside in Boston, Massachusetts, but I'm originally from Chennai, and that's where I did my undergrad and stuff. And I recently finished my PhD from Dartmouth, as the host told you guys. And I worked with Sean Smith and Sergey Bratus for my PhD. And these are my broad interests. I'm broadly interested in formal verification, file formats, weird machines, parser exploits, all of those nice stuff. So but in this talk, I'm going to be presenting something from my PhD work. So I would really like to thank them and my collaborators at SRI International and also at PDF Association, because this is work on PDF. So then, of course, we had to have PDF Association in the loop because they maintain the spec, and of course, the funding agency. So I guess, why would anyone even bother checking if PDF files conform to the spec, right? So the real reason is just that, why not? Of course, people are doing things wrong. The short answer to the title of my talk is, of course, no, right? If you guys didn't know. So when you think about why PDFs, the first thing that comes to mind is a conversation that I had with my advisor, who happens to be Russian. So any conversation always starts off with a long Russian story or a rant about Soviet Russia. And then he was like, lately we've been thinking about PDFs. Have you thought about it? Because how do you even write a parser to validate PDF files to ensure that any PDF file that you're consuming is fully valid? And I was like, don't they embed like several other formats, starting from images to literally everything under the roof? Like, you can embed pretty much anything inside a PDF file, right? So then why would anyone even want to do it? But often, if something goes wrong, if there is an exploit, a crafted file, it is a Microsoft Word document or a PDF file of sorts that triggers a vulnerability. So it is always one of these three. But then in this talk, I'm talking about just PDFs. So has anyone over here actually used a text extraction tool on a PDF file? Anyone? Not OCR, a plain text extraction tool. Cool. So let me actually show you 3 of them and their output on the exact same file. And let's see if you spot something interesting, right? So I'm guessing you can see this because it's pretty big and clear. So there are 3 tools that I'm using over here: PDF to text, and then PDF to text.py, which happens to be from PDF Miner, and then GoScript, which happens to be from Mutool. So then these are the 3 broad files. These are the 3 files I'm going to test. And let me just quickly show you the file as well, just so that you know what to expect. So it's a SEC file. I collected this file from Common Crawl, so it's totally okay. Don't worry about the names and stuff. It was from Common Crawl. So you see that there are tables, and it's basically just 2 pages, right? So you just expect similar text to appear. And now let me just show you what the 3 outputs look like. So the one to the leftmost is GoScript. The one in the middle is PDF Miner, and the one to the right is PDF to text. Do any of them look like the actual file? I would think that GoScript looks the closest to what was in the actual file, but PDF Miner looks far away, like there's no white spaces, it's all fully disappeared. PDF to text is close enough, but it's still not really there. So what am I really trying to say here? These three tools are supposed to do the exact same task. They read the exact same spec. They've all read PDF 1.7 spec. Although PDF 2.0 is the latest one, they've all implemented PDF 1.7. But somehow, when you actually look at the output, they're all different. How the hell is this okay? Yeah, so I guess this is where I introduce what language theoretic security, which is the area I work on, is, which is also known as LangSec. And in my talk, I'll also be giving you an overview of a PDF file format, how a PDF file looks, what structure does it follow. And I'll also be talking about the tool that I built called Sparta and PDF Fixer, which sort of fixes these commonly seen bugs in PDF files. So to motivate the problem of why do we even have a field of a subfield of security called language theoretic security, it comes down to, it all started sometime around Heartbleed 2014, when there were a host of vulnerabilities in OpenSSL, and this was a real issue because to just describe it in short to those of you who don't know about Heartbleed, the OpenSSL protocol has a particular feature called a heartbeat, where what happens is that you can keep a connection alive. So you can send a message stating how many characters you're sending, and then you receive that identical message back. So it's basically an echo server of sorts. So you are basically sending, in this example, you're saying that you're going to send 6 letters and the string potato, and then you expect the server to return that exact string. But what in practice happened was that there was no check between how many characters you were sending and how many characters you said you were going to send. So for example, you can say that you're going to send 500 characters, but end up sending just 3. And then what does the server do? A very intuitive answer is that, of course, the server should have rejected it. This is such a dumb bug. But in practice, that didn't happen. And that sort of raises a deeper question. Do people actually fully validate input that they consume? Is the real question here. And it's something similar that we saw in this particular bug of Pegasus that was called forced entry. And this was also exposed in 2021, where the attacker used PDF files that were disguised as GIF images. So they were and they sent it to a PDF library. A PDF library should have directly rejected a file that was a GIF file and not a PDF file, but it didn't. So again, the same question, why not actually properly validate? Why can't you validate? So any system that actually accepts input, we know that we test it against all the expected input, or at least a subset of expected input, but we don't really test it across all possible inputs. And often we don't know what is going to happen, because you can't theoretically test for all possible input. And often we use tools like fuzzing that will explore a search space, but it's not going to get everything. Formal verification you can use, but then what will happen is that you have some preconditions and you're just checking within those bounds. You're not really exploring everything possible. So the parser is really the what stands between invalid input and the rest of your program. So your parser is going to take unstructured input of any sort and validate it, and then transform it into something that the rest of your program can consume. So those are called well-typed or structured objects. And improper input validation is really one of the most common weaknesses that we keep seeing in the MITRE databases. And incorrect and insufficient parsers are what lead to vulnerabilities, which is why I was saying that the parser is really what stands between you and invalid input, and hence you have to pay a lot of attention to it. And you might think that if I use a memory-safe language, why do I care, right? But there is another class of vulnerabilities called the parser differentials. For example, what I just showed you, where the same parser is consuming the same, different parsers are consuming the same PDF file, but they output 3 completely different things. So that's not okay, right? Because we have seen in the past that parser differentials can lead to really, really serious issues. For example, in this particular case that I have on the slide, Dan Kaminsky, Len Sassaman, and Meredith Patterson in 2010, they demonstrated that if you just put a simple null character in between of within a URL, different X509 parsers or certificate parsers get tricked into doing different things. And interestingly, 2 of these 3 outputs that I have over here were within the same library. The same library has 2 different parsers for the same thing, and then they both have different outputs. If you're doing the same thing, why do you have to implement it twice? So yeah, basically the idea is that it should have the same output. And iOS had a very similar issue where they had 3 different XML parsers. They had actually 4, but 3 of them had issues in how they read comments. And XML was really how they do this thing called entitlements, which is behind their entire iOS permissioning system. So the idea here is that an adversary can really craft a permission where one parser sees that it's a comment, whereas another sees that it's a legitimate permission. So you can trick the user into seeing something, whereas the actual permission underneath is something completely different. So for those of you who have taken like a formal language theory course and know about Turing machines and such, checking the equivalence of these parsers, right, is undecidable if you go beyond a certain language class in the Chomsky hierarchy. So it really cannot be done, and which is why you really need to stay within the deterministic context-free or the regular boundary. You can't really do that in PDF, but in practice, at least for networking protocols, this is something that you should strive for. So what really is language theoretic security, and why am I talking so much about it on and on? So the motivation behind it is that offensive research and defensive research are sort of go hand in hand, and defense is offense's child. And so language theoretic security sort of takes inspiration from both defensive and offensive security, as well as formal language theory. Like the result that I just showed you, where you cannot really show equivalence of 2 parsers, is something that's really important when you're writing your own parser. And hence, parser toolkits also need to know and have knowledge of these issues. So let me just boil down to what are the core principles behind LangSec. So the basic ideas are that you need to fully recognize your input before operating on them, and all input that the rest of your program is going to consume has to be fully recognized and validated, and any input that is even mildly malformed, you have to reject. You cannot be super permissive. If there are reasons that you have to do that, you need to update the spec and make the spec more permissive in the first place, and not just make your implementation violate the spec. You need to keep the input language as simple as possible. You shouldn't complicate it too much, because sometimes that's the place where vulnerabilities even stem, because things like weird machines, if you guys have heard of that concept, stem from the fact that you have a very complex input format. The third is something that practitioners really can implement even today, which is that you really need to separate your parser from the code. A lot of people who do pen testing as well as security audits attest this, that the parser is really where you want to find vulnerabilities, and you often will end up finding it. And hence, if you actually separate the parser entirely from the rest of the code base, you can essentially ensure that you're looking at the right place, and you're looking at only the parser at that point. When you mix everything, it's very difficult to know which portion of it is the parser and which is actually operating on the code. So to actually describe the same concepts in a language that hackers understand: full recognition before processing, computational equivalence for all protocol endpoints, which also applies for file formats and network protocols. We need to stop weird machines, and no more Turing complete input languages. The place where the LangSec paradigm comes in is the input validation layer M over here, which is basically trying to validate any input that's going through and rejects the set of possible inputs and separates it from the set of expected inputs. Sorry. So you might be wondering, all this was nice in theory. I'm preaching something. This is nice. How do you really do this in practice? So in practice, you can use two tools, two families of tools actually. One is called parser combinators. And what they do is that they implement code that looks like grammar. So you can have a formal grammar or a specification, and a parser combinator toolkit actually allows you to describe a format just like you would in a grammar. So what you see over here is an example of a DNS specification, where you start with an ID field, which is 16 bits or 2 bytes, and then followed by 1 bit and 4 bits and so on. The h_u int 16 is of course a 16-bit unsigned integer, and so yeah, basically you can append everything into a large sequence operation. And another paradigm that you can follow is that of data description languages, where what you're doing instead is you're generating code from a grammar specification. And Kaitai is an example of one, and that's the example that I have on the right, which uses YAML syntax. You can use something like DFDL, which uses XML's XSD syntax. And Kaitai is the one that actually generates tons and tons of, generates code in tons of programming languages. And that's certainly a very cool project that I really encourage you to check out. And what do I mean by it looks exactly like the specification, right? This is what the DNS RFC message format looks like. And you can see clearly that you have an ID followed by a QR, followed by an opcode and everything else. So then you would see that all of these three sort of match clearly. And it's basically the same thing implemented in Hammer as well as in Kaitai. The only difference in Kaitai is that they have defined a separate type for flags, and all of these get basically compressed into that one type. So that was hopefully a quick LangSec introduction, and now I'm actually going to move on to PDFs and how a PDF file actually looks. So the PDF spec, the latest one is from 2017 or 2020, depending on when you bought it. So there is a PDF 2.0 specification from ISO, and that's right now like 971 pages long. You can ask me, did I read all of it? Probably not. I read most of it because I had to. What you see on the right is a poster from Corkami or Ange Albertini, where that sort of describes what a PDF file looks like. So who of you have actually looked in binary what a PDF file looks like? Anyone? One. Wow. Okay. There's more. Nice. So what you see on the right is what a PDF file is, and there's basically a header which specifies what the version is, which can range from 1.0 to 2.0, and there are a few numbers that are skipped in between, but that's broadly what the range is. And then there are objects inside the PDF file. And then there is a trailer, which has a certain syntax, and there are some fields that are mandatory, some fields that are optional. So how would you really parse this file? Because the trailer is what says where the cross-reference table is. The cross-reference table is a table that says where all the other objects are. So it's basically an index. And because that's at the bottom of the file, and the location of the cross-reference table is stored in the trailer, you have to start reading the file right from the bottom. So you parse a PDF file from the bottom, and you read these values, and then you have to jump to those values and read and then read the objects individually. So Yeah, so that's the diagram that you have over here, where you start with the trailer, then move to the root, and then you start traversing the individual pages. There is this one really special object, which is also called a root or a catalog object, which is really special because that's what contains a lot of metadata and a lot of interesting information. And the specification says that it can contain up to 33 keys, but there are only like 2 or 3 that are mandatory, and most of them are just optional keys. So let me quickly show you what a PDF file may look like. Right. So as I described earlier, it starts off with a header right at the top, which is the version number, and then you have a bunch of objects. So 10 obj is basically the object number, generation number, and then just the keyword obj, and it ends with an end obj tag. You may ask what these characters are, this greater than, less than, before the, after the obj and before the end obj. And those denote basically a dictionary object. So PDF contains dictionaries, arrays, and a lot of other types. Yeah, so you'll see that there are several of these, and then the most interesting one that I wanted to show you was the trailer. So the trailer is also a dictionary that's denoted by these signs, and then there are 2 keys over here, which is the root and the size, right? The root, the keys are denoted by a slash sign, which, so this particular type is called name type in PDF, and the root is basically just the name or one of the keys of the dictionary, and then size is the other key. And this is basically an indirect reference. That means an object called 10 exists somewhere else in this file. So it's basically saying that root is the object 10, and then size is just the number 5. So now let me actually show you what the spec says. So there is, interestingly, there is a machine readable version of the spec, and it's available on this link of the PDF Association. And what I particularly wanted to show you was the file trailer, because that's what I just showed you. And if you recall what I just showed you, there was a size key and a root key, and those are the 2 specified as required in the spec. And pretty much everything else, so the ID is required in certain situations. We clearly did not have a version 2.0, we had a version 1.1, and everything else is pretty much just optional. Cool. So that hopefully was interesting, and shows you how the Arlington DOM actually matches to the spec. The DOM is entirely in, DOM stands for Document Object Model, and that is entirely in TSV files. There are totally 515 for version 2.0, and it contains a lot of rows and a lot of columns. What links are over here are the most interesting thing, because they are user-defined types that correspond to another file. So there's another file that's going to contain more information. Yeah, so let me now describe a little bit about the Parsley project and Sparta, the tool that I'm here to talk to you about. So the Parsley project is basically an entire Rust system where we are syntax checking a file, and then applying types to it, and then extracting text or transforming it. So what do I really mean by we generate Rust code, right? So then we are basically taking the TSV files, and then we generate, we have an API, and we generate code that corresponds to that API. And our type checker essentially does a breadth first search starting from the catalog dictionary. Yeah. So the DOM validator, so the Sparta checking tool itself contains a validator because we wanted to first make sure that the TSV files themselves were valid. And what we found was that when we compute these stack dependencies, because you have pointers and links, right, within the spec itself, we found that there were several inconsistencies that we had to report to the PDF association, and only then we were able, only once those were fixed, we were actually able to generate error-free Rust code. And here is actually an example of what the type checker API itself looks like. So you have basically dictionary required keys or optional keys on the right, and then we enforce the specifications that are present in the Arlington DOM. So yeah, let me show you what the Yeah, so here's what the catalog dictionary type looks like. So essentially, it contains a bunch of assignments that are right at the bottom of the file, and then we have individual declarations here. The second argument over here, which is true or false, denotes whether it's going to be an indirect reference or a direct reference. So what I mean by an indirect reference is that the object is going to be somewhere else. And if this value is set to true, that means that this particular object is going to be somewhere else. And we basically, so the optional key over here, the OPT key, specifies whether this particular key is going to be optional or mandatory. And this is how we actually define a large dictionary, like a catalog dictionary, because that's the one that has like 33 keys or something. Yeah. Yeah. So when we actually ran this tool, right, we found several issues that were really common. My goal in this talk is to not name and shame people, because that's already been done, and we've reached out to them and told them to fix things. And often what ends up happening is that the spec is weakened to accommodate some big players who may have made these mistakes. So that's why you see on the outcome column quite often the specification was fixed, because some big players violated the spec. It's very difficult to fix it now because there are several files in the wild already, so it's not going to happen. One thing that's of particular interest over here is the page tree node key is missing. So I'll get to that in the next slide, but before that, there is the language key as well. And the language key is a key that's present in the catalog dictionary, and it's very extensively used because it specifies what language the file is supposed to follow. And the reason I say that that's important is because without knowing what language it is, how do you extract text? Because sometimes the language might be a right to left language or a top down language, and you really need to know what language it is before you can extract text. So the reason I said that the page tree nodes are quite interesting is the spec, right? So the spec says that there are 3 keys that are required, and the parent key, except in the root node, it's not permitted in the root node, but any other time it's required. So the type key, the kids key, and the count key. And what you see on the left is a file that's is an object that's from a real file, where you can clearly see that one of these keys are not present. And you might think that, what's the big deal, right? Why should I? It's such an easy thing to fix. Let me actually show you a file, right? So I'm just going to call our PDF printer, which is the tool that that actually type checks the file. And you'll see that we found a missing count key, and it's at a certain location, 74E. So I'm just gonna open this file and show you that particular location and so show you this key missing. Yeah, so you see that it only has a kids object, a kids key and a type key, and hence the type checker was right in finding that this file is invalid. But is it really invalid? Like, you're again thinking this is such a small bug, it should, yeah, don't open. So we also have a version of this particular type checker that fixes bugs inline and then writes the fixed PDF to a separate location. But of course, we fix only certain issues like these keys missing. And we run it again in the fixed mode, and again, we find something else. So yeah, this time it's the same file. Yeah, so it's basically a page object, and again, the parent key is missing in this one. And the parent key is actually mandatory in a page object. So again, the error is correct, and the file is invalid in that sense. But the most interesting thing here is, of course, were we able to successfully fix it? And it writes a file in its current state to on this particular path. And when you open it, you can read a lot of these things. So yeah, we were able to successfully fix it. And to just show you some text from the file, you would see that this particular object, 20obj, it's called the info dictionary or the information dictionary, and that reveals the name of the person, like SOPHIA. So yeah, you can technically see some metadata from the info dictionary, including the title of the PDF and other things. Yeah. So yeah, it's the same file, and we were able to successfully fix it because we looked for this particular bug and we fixed it. Right. So yeah, that was the demo of the type checker and us fixing it. We did actually evaluate it on another large data set actually. We collected a bunch of data from archive, 3 months actually almost, and it was over 100 gigabytes of files. And there were certain types of type errors that seem to occur a lot in LaTeX files. And LaTeX seems to be doing fonts absolutely terribly. But more commonly, when you look at 1 million files from Common Crawl, the most common bugs that we end up seeing are incorrect language keys, which are terrible for text extraction, page tree node errors, because they cannot be rendered at all. So there are 20K files that most other tools might think are fully valid, but most tools, there are a lot of tools that can't even render these files. And then, of course, page mode keys, which denote whether it's 2 column, 1 column, those type of things. And null references are another thing where you have a reference to a certain object, but the object doesn't exist in your file at all. And even that's something that's really common. Again, as I mentioned earlier, I don't want to name and shame companies or tools that actually commit these errors, but LaTeX tools definitely do a lot of these. So yeah, to actually fix these bugs, we have an engine where we read a set of these reducer rules, that's what we call it, reducer, and we apply these transformations to an intermediate language that we have, and then we actually write the modified IR that we have using a serializer, and we produce a transform PDF file that's canonicalized, and that's simplified and has only one cross-reference table. So technically, a PDF file can have many cross-reference tables with links, and we are trying to simplify that as well. So yeah, this was one thing that I just showed you that we can actually fix as a set of our reducer rules. We have a lot of other rules as well. For example, if there are some of the font keys that are missing, we can fix those as well. So yeah, when would you even want to use such a tool? If you want to normalize PDFs, and there are certain bugs that are causing differentials. You want to normalize it, you can do this. If you want to redact some information, as I showed you, the info dictionary contains operating system versions, creation tools that were used, author names, and what we do is we actually redact all of that from the info dictionary. And another thing that I actually did was I was also able to generate a file that causes the denial of service attack in MuTool by creating a certain loop in the catalog dictionary. So yeah, we are using the machine readable spec, but of course there is some resistance to incorporating this in public tools. But there is a push to use machine readable specs such as DFDL and Kaitai in the wild, where you want to write the entire specification in a data description language. But there is some resistance to this, obviously, because DFDL and Kaitai are not powerful enough to even represent something like PDF. PDF is so complex that you can't even represent most of the things in PDF in a language like DFDL or Kaitai. So we do need some new languages that can capture the complexities of a PDF file format. So yeah, PDFs in the wild are crazy. PDF spec and what PDF processors do are completely different. And so yeah, that was my talk. Thank you. Thank you for listening.
Hello. Do we have any questions?
Prashant, that was amazing. I just wanted to know the results of the 40,000 files you shortlisted.
I can't hear you properly, sir.
Is it audible now?
Yeah.
Okay. I wanted to know the results of the 40,000 files, the sample you took. What was the output of that? Were you able to fix all of them?
No. So the thing is that most of these files were, of course, vetted by Archive itself. So Archive actually compiles most of them. So most of them did not need any fixing. And these were type errors that we were absolutely not able to fix because we had never even seen them. Because this was a very, we technically oversampled LaTeX files, right? So then this was not something that we were able to fix at all automatically.
So if we talk about the percentage you were able to fix from the right set of this 40,000, what would that percentage be?
The thing is, most of them didn't need to be fixed in case of Archive. But I don't have that exact number. I can get back to you on that.
No problem. Thanks.
Yeah.
Any more questions?
Hello, sir.
Hi. Yeah.
What about PDF injections?
What type of PDF injections?
Like inserting JavaScript, like alert, submit form.
Yeah. So they are there, and those are usually completely valid in the spec, right?
How to exploit it? Right?
Sorry?
How to exploit it?
How to exploit what?
Yeah, from P4 to P1, P2. Yeah.
Right. So the thing is that you can put arbitrary JavaScript inside a PDF file. And how to exploit it or even do we prevent it was not something that we were interested in doing because we were trying to enforce the spec. And so we are saying that you can do it. Yes, of course.
So thank you.
Yeah.
How do you think we can make a strong spec? Like, sorry, am I audible? Yeah. How do you think we can make a strong spec? Do we need to hide the language until it has a perfect spec, or what do you think is better?
So there is the thing that my personal opinion would be that yes, you have to start making things stricter. You have to name and shame people. You have to force people to use the machine readable version of the spec. But there is the other side, which I understand the market economics here, and it's not going to happen. So what's going to continue to happen is that big players will continue to make mistakes in new features, and then we'll keep reverting back the spec. We'll keep making the spec weaker and weaker to accommodate all the mistakes that others are making. Yeah.
Does anyone else have any questions?
So have you taken a look at the PDF/A specification for archival use And is the situation there significantly better than for normal PDF?
It's much better because PDF A was written with the whole goal of making it machine readable, but some ongoing work is actually understanding what percentage of files in the wild are even PDF A compliant, and it's less than 1%. Like, so PDF A is so strict that it's less than 1% of files that would be compliant with that strict version of the specification. Yeah.
Any more questions? I think
we're good.
Cool. Thank you all. And if you still have some questions, you can come and find me.
There's one more question.
Yeah, sure.
Like where we can know more about LangSec.
Sorry?
LangSec, language security.
Yeah. You're saying you want to know more? There is a website called langsec.org, and you can go there and see some seminal papers. And there is a grad program at Dartmouth where I did my PhD, and they are looking for PhD students. So if you are interested, then, and if you're interested in grad school, you should apply. Yeah.
Thanks.
Yep. Thank you all, and you can come and find me somewhere grabbing some coffee. Yep. See you all. Bye.